Hi everybody. It is week 5 of our class, and we are going to be talking about basic concepts of probability this week. And the first topic for us to talk about in terms of probability is an introduction. We are going to introduce the idea of probability and talk about some approaches and properties of probability. So when we talk about probability, the theory of probability is really the foundation of statistical inference. In the beginning of this semester, we talked about the difference between descriptive statistics and inferential statistics, and that inferential statistics, we are looking at our data and we're trying to make draw conclusions from our sample about our population, and we're usually comparing two things and looking for answers to our questions. And so probability is really the foundation of being able to accomplish anything in terms of inferential statistics. And in the health sciences, we use probability to talk about things all the time. We talk about things like the chances of an event happening, like a surgery may have a 50-50 chance of survival. In health-related research, we use probability in hypothesis testing. For example, if we want to determine if the improvement we see in a patient is due to just chance, or if it's actually due to some new intervention that we're testing. Probability is often expressed in percentages. We hear a lot about things having an 80% survival rate or something like that. But probability is more accurately expressed as a fraction. And when we express probability as a fraction, we have to understand that a probability of 0 means there's no chance of something happening. A probability of 1 means that it will always happen. And most events will have a probability between 0 and 1. Now, we have two main approaches to calculating probability or thinking about probability. There's something called the objective approach and the subjective approach. And the subjective approach we'll talk about later is kind of frowned upon in terms of statistics, but there is one subjective approach that is used a lot in biostatistics, and we won't actually talk about that until next week, until week 6. But so most of what we're going to be talking about is objective probability. Objective probability can involve the repeatability of an event. Usually all possible outcomes of an event have an equal likelihood of occurring. But the key with objective probability is that we're not really using any outside knowledge, right? We're really using just the data that's in front of us. An example of when objective probability is the right choice, if we want to know what is the probability of drawing a heart out of a deck of playing cards, right? We don't need any outside knowledge to know that. All we need to know is how many playing cards there are and how many heart cards there are. Okay? The use of subjective probability can be helpful to answer certain questions where prior or relevant knowledge of the circumstances is going to be necessary to answer the question. But the thing that's important is that we are estimating the likelihood of a possible event. We can only make estimations with subjective probability. We make educated guesses. Okay? An example of when subjective probability could be used, if somebody asks you what is the probability that we'll have a cure for cancer in the next 10 years, there's no objective approach to answering that question. What you're going to do is make a subjective estimate based on your knowledge, based on the available knowledge, and it's really going to be an estimate, and that estimate might be wildly incorrect, it might be very inaccurate, or it might have some merit to it. So the subjective approach is used with a lot of caution. It's not really taken very seriously, but as I said, next week we will look at one example of the subjective approach. It's called Bayesian theory. that we use in biostatistics, right? We do use in the health sciences. But pretty much everything we're going to talk about this week is the objective approach. So a couple of things to define here. We want to define what is an event, what is an outcome, and what is the sample space. So an event, in terms of probability, is any collection of results or outcomes of a particular procedure, okay, or a particular study. A simple event is an outcome of an event that cannot be further broken down into any simpler components. Okay? And the sample space is the space that a procedure occurs in. Okay? The sample space for a procedure consists of all the possible simple events. Okay? So all the possible outcomes cannot be broken down any further. They all exist within the sample space. So if we look at this table here, what we're looking at is an example of, let's say a family wants to have 3 children, and they want to know what are the possible combinations of girl and boy babies that they could have. Okay? If they have a single child, right? That's a single event. And so if they have a boy, then it's a boy. If they have a girl, it's a girl. So the procedure here is a single birth. The example of an event is having a boy or having a girl. That's the simple event. It can't get broken down any further. And the sample space is all the possible things that could happen, all the possible outcomes. And it's, as you can see, the list of possible outcomes with a single birth is a boy or a girl. Okay. Now let's consider that same family who chooses to have 3 babies. So 3 births, that's the procedure. An example of an event is 2 boys and 1 girl, right? That's one single simple event. 2 boys and a girl. The sample space is the list of all of your possible outcomes. And so here we've got boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes of a single, of this procedure of 3 births. And notice that we are, the order that the babies are born in is important. Okay, so we're listing out all the combinations in terms of birth order. And that's our sample space. It's all the possible outcomes of our procedure. We also have to be aware of the expression and notation. How do we see probability when we're working with it in our calculations? Okay? So probability is expressed as a capital P. So capital P stands for probability. Sometimes we have to denote what we're looking for in terms of the probability of something. So A, B, C are going to represent our specific events. So P bracket A, or excuse me, parentheses A, end parentheses, that's going to denote the probability of event A occurring. Okay. So that's what we're going to see as we're working with these problems. And then here on the left, we've got our scale, right? So we are going to really be talking about probability as a fraction. And that fraction is going to be somewhere between 0 and 1. So 0 in terms of probability means that that event is impossible. It is not possible. And then 1 in terms of probability means that it is certain. It always happens. And then our probabilities are going to mostly fall between 0 and 1. Okay? Between 0 and 50, right? As that number approaches 0.5, it increases in likelihood. When we get a probability of 0.5, it means there's a 50-50 chance. It happens 50% of the time. And the other 50% of the time, it doesn't happen. And then as we get above 50% or above 0.5, we're talking about things becoming more and more likely. Okay. Now, because we're looking at probability in terms of a number between 0 and 1, we have to have a rule about rounding. Okay. So when we express the value of a probability, whether it's a fraction or a decimal, we round off that decimal to 3 significant digits. Okay. So that's our rounding rule when it comes to probability. So for example, if we calculate a probability and we get 0.44503239, right? And this was an example in your textbook. That number has 10 significant digits. There's 10 numbers that come after that decimal. So we're going to round that value to 3 digits. So it's going to get rounded to 0.445. If we have a probability of 1/3, okay, we can leave it as a fraction. We can just say the probability of something happening is 1/3, or we can round it to 0.333. We're not going to round it to 0.3. We're going to round it to 0.333. And then if we have a probability of 2/8, it can be expressed as 1/4, right? Because that's the same as 2/8. Or it can be expressed as 0.25. And we don't have to put it as 0.250, okay, because that's not necessary. All right. So that's how we are going to express our probabilities when we calculate them. So this objective approach to probability, this is mostly what we're going to be dealing with. There is 2 categories of this objective approach. There is what's called classical probability or a priori probability. And this is where an event has multiple possible outcomes and all the outcomes are equally likely. An example of this is we roll a dice and we get one of 6 possible numbers that can equally likely happen. Okay. And then number 2, we have what's called relative frequency probability or posteriori probability. And this is when there is some procedure, there's multiple outcomes, and these outcomes, the procedure is repeated a large number of times. And we want to know the probability of a specific outcome occurring. Okay. So let's consider each of these categories, classical versus the relative frequency. So first off, we have our classical approach. And what's absolutely necessary with the classical approach is that all outcomes are equally as likely. Okay? All outcomes are equally as likely. So if a procedure has n number of different simple events that are equally as likely to occur, and if A can occur in S different ways, okay, then the probability of A happening is equal to the number of ways A occurs over the number of different simple events. Okay? So PA is equal to S over N. So, and what's very important that we have to make sure is when we're using the classical approach, we always need to make sure that all outcomes are equally likely. Okay. So, let's look at an example. Okay, let's look at an example. Let's go back to what we looked at before, which is our family who wants to have 3 children and wants to know, what are the combinations, possible events that can happen. So a couple is planning to have 3 children. They want to know the chance of having different combinations of genders. If boys and girls are totally equally likely of happening, which is true, then there are 8 possible simple events that are equally as likely. Okay. And so assuming that those boys and girls are equally likely to occur, find the probability of getting 3 children all the same gender. Okay. So here we have our sample space. The sample space gives us 8 possibilities, okay, all equally likely of happening. And there are exactly 2 outcomes in which 3 children are of the same gender. Okay? Boy, 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 and girl, girl, girl. So there's only 2 possibilities. So you can use the classical approach to get our answer. Okay? So the probability of 3 children of the same gender is equal to 2 possible combinations over 8 possible combinations in all, which is the same as saying 1/4, which is the same as saying 0.25. The other category of this objective approach of probability is relative frequency approximation of probability. And this is where we conduct or observe a procedure and count the number of times that event A occurs, and then a probability of A, PA, is then approximated as follows. So PA is equal to the number of times A occurs over the number of times the procedure was repeated. Okay. So let's do a practice problem looking at relative frequency probability so we can get a sense of what we're talking about. So find the probability of dying, I know it's very dark, of dying when doing a skydive jump. Okay. So, and then we look at for the data, and we're not going to, this is not subjective, we're actually going to calculate and make an estimation, a more accurate estimation. So we look at data in the recent year. There was about 3 million skydive jumps, and 21 of those skydive jumps resulted in death. So we use the relative frequency approach. So the probability of a skydiving death, right, P skydiving death, is equal to the number of skydiving deaths over the total number of skydiving jumps. And that's 21 over 3 million. So 21 divided by 3 million is 0.000007. Okay. So here the classical approach can't be used because the 2 outcomes, dying and surviving, are not equally likely. Okay? And a subjective probability can be estimated in the absence of historical data. Okay? So we're not doing a subjective probability, we're using relative frequency probability because we have historical data. We have data from the last year that 21 deaths out of 3 million occurred. So now we can estimate that moving forward in time, the probability of somebody dying from a skydive jump is very, very small. Notice our 3 significant digit rounding, you know, this number would actually get rounded to either 0 or 0.001, okay, to actually represent how small the risk of dying is for these skydiving jumps based on last year's numbers. So subjective probability, if we don't have historical data to answer the last question, we could just try to figure it out, make an educated guess. And that's what subjective probability is. So, for example, what is the probability that you will get appendicitis in the next year? So we could probably find past results and use relative frequency approach. We could find out how many people in the last year or several years had appendicitis. But for now, let's try to answer this question without any historical data. Okay? We're going to make a subjective estimate. So my personal experience is that the probability is very small, okay? Because I've never had appendicitis. I've never known anybody who's had appendicitis. So let's estimate it to be, let's say, 0.001. This is equivalent to the chance of 1 in 1,000. So that's one possible answer. But depending on our knowledge of the relevant circumstances, that estimate might be reasonably accurate If I was a emergency room doctor, my estimate might be better than if I was just a random person. Okay? So it might be reasonably accurate, or it might be grossly wrong. It might be absolutely wrong. And this is why subjective probability is sort of looked down upon and frowned upon, because it's really a guess. It's really a very, very subjective guess. Okay? So most of what we're talking about is objective approach to probability, and let's do a practice. Okay, let's do a practice on doing one of these things. So the context here in this example, in a study of high school drivers, U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days. Okay? And 4,720 did not text while they were driving during that same period. Based on these results, if a high school driver is randomly selected, find the probability that he or she will text while driving during the whether he or she texted while they were driving in the previous 30 days. Okay? So we're trying to figure out, of all of the high schoolers that were surveyed, okay, what is the chance that they texted while they were driving? Okay. So when we're doing probability, we're always first trying to figure out what is our denominator. Okay? What is the total number that we are drawing from? So the total number is the number of high schoolers that texted while driving, plus the number of high schoolers that did not text while driving. So that's 3,785 texted, 4,720 did not. If we add those together, we get 8,505. That's the total number of drivers in our sample. Now we can use the relative frequency approach. Okay, the relative frequency approach. So texting while driving is what we're looking for. So the probability of texting while driving is the number of drivers who did text while driving over the total number of drivers. That's 3,785 over 8,505. And that's equal to 0.445. So there is a 0.445 probability that if a high school driver is randomly selected from that sample, he or she texted while driving in the last 30 days. That's pretty close to 0.5, right? So that's almost a 50-50 chance. Okay. Sometimes we need to calculate the probability that an event does not happen. Okay? So events can either happen or events cannot happen. And that is that phenomenon, right, where events are either happening or not happening, is something that we describe as complementary events. Okay? A complement of an event is when that event does not occur. So when we look at event A, okay, the complement of that event is called A with a line over it. Okay, so complement of A, and that consists of all the outcomes in which A does not happen. Okay, so let's go back to our skydiving example. We had 3 million skydiving jumps, and there were 21 deaths. So the complement, the number of skydiving jumps where there was no deaths, is going to be equal to 3 million minus 21. Which is the same as saying that there were 2,999,979 jumps where people survived. So if we wanted to calculate the survival rate, right, the probability of not dying when making a skydiving jump, we take 2,999,979 over 3 million, and that gives us 0.999993. Okay. So the probability of not dying when making a skydiving jump is very, 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 very high. Right? 0.9999999. So in review, okay, in terms of what we talked about here, we talked about how probability of an event is expressed as a fraction or a decimal, and a number basically between 0 and 1. Okay. The probability of an event that is impossible of happening is 0. And the probability of an event that is certain to happen, will always happen, is 1. Okay. And when we are talking about the probability of something, the notation is PA, meaning the probability of event A. And when we look at PA with a line on top, that is the probability that the event will not happen. That is the complement of event A. Okay. So we're gonna so far we've talked about the mostly the objective approach in using the classical method and the relative frequency method. We did a few examples. Next video we're going to expand on that.